Afternoon, welcome. We started today on Russell Standard Time, so now we're on Roger Standard Time, so it's the same acronym. Welcome to Bluff Your Way in x64 Assembler. So I'm not quite sure what you're here for, what you're expecting. Maybe you just want somewhere quiet to sit after lunch or work on your presentations later in the week. But I thought I'd start by asking, how many of you have ever written any assembler at all? You're probably overqualified then, but okay. How many of you have never written any assembler? How many of you have never seen any assembler? Okay, so there's a disjoint between the people that have written the language and the people that have seen it, and that's very common. In my day job, for those of you who don't know me, I'm a recovering C++ programmer, and I very, very rarely write assembler. I think the last time I was paid on a contract to write assembler was about 5 years ago. We needed to do something that couldn't be done in C++. There are things that can't be done in C++. But I do see a lot of assembler. And some years ago, there was a kind of enough assembler to get by that Matt Petrick wrote for MSDN. Does anyone recollect that from back in the day? Which was a bit about the x86 32-bit assembler and enough information to kind of get you started. One of the problems with assembler is few people write it, few people publish books on it. It's really non-trendy. I mean, I was half expecting no one would come because everyone will be out doing flashy WYSIWYG stuff on the web. But it's still important. So I'm hoping that by the end of this session, you'll have a little bit more confidence to go and play and experiment. There's lots of information out there. You can download the Intel or AMD reference documents, hundreds, literally, of pages describing in minute detail all the opcodes and things. But if you've got no understanding of what's really happening, where do you start? How do you make sense of all this information? So where does it fit in? Most of us program up here in some high-level language. What languages do people use? I'm guessing some of you use C++? Yeah? C#? Higher up still, kind of Python interpreted languages, yeah, you know, JavaScript. Getting a long way away from reality up there, aren't you? As Joel Spokesy wrote, probably quoting somebody else, because that's the way most things happen, all non-trivial abstractions to some degree are leaky. You can't really hide what's beneath you. You can try, and you can often do a fairly good job. But there are times when you just need to have some understanding, or having some understanding of what's happening in the next level down helps you with the task you're doing. So you can go off and write web pages and not have any idea about network protocols, HTTP, but some understanding of what's happening in that space will help you at the higher level. And the same, I think, with high-level languages, and certainly compiled languages, some understanding of kind of how this stuff works at a lower level can be helpful in making sense and doing good decisions at the higher level. And also, of course, when it goes wrong and you end up with, you're in the debugger, or you've got a call dump. Who gets call dump still? Yeah? Programs keep crashing. It's very sad. And you're left with what the debugger makes of this pile of binary noughts and ones. And it's not that common that it nicely tells you what the high-level code was that you wrote. It tends to be something rather lower than that. So I thought I'd take a layered approach, very, very simple, very high level, at a program that might look vaguely familiar. There we are. An old friend, Hello World. Who's written that in the past? Who's compiled it successfully? Yeah, good. Who's run it? Who's had it crash? Yeah, it is quite worrying when Hello World crashes. We were trying to use sanitize with Clang, and it just core dumps when it starts, which is a bit sad. So you start with something very simple, just a few symbols, and you run it through the compiler. You've also, of course, got a header file which got included. Shed loads of code that you didn't write. Well, is Marshall in the room? You probably didn't write. And you certainly don't want to read because it's not that readable, unless you can't sleep, when it might have a great purpose. And the two things go together, and out of the bottom end comes some binary. or conceptually comes from assembler language. Now, whether there actually is any assembler language involved in the process, of course, you probably neither know nor care. But conceptually, at least, it goes from a high-level language to assembler, and then stuff happens and it gets linked together. And there was a talk before lunch about linkers, so anyone who went to that can refresh their memory, and you end up with machine code. What does the chip know about assembler? Nothing. It knows about bytes, and it reads memory, and it deals with them at that level. But I would not really like to debug code like that. That's so 1980s, when we had a full-screen interactive debugger that produced things like that on the screen. And you had to know that B801 was load nibble R0 with 1 or whatever it was. We don't want to be at that level any longer. But also, down at this machine code level, you're making use of libraries, perhaps in the GCC world, libstd, C++, libc, etc. Oh, and then below that, still, you've got an operating system. And somewhere, I believe, there's a rumor that there's some hardware. But that's probably on a blade somewhere else on the planet. You may not be quite sure where it is. And we're so used to doing this that we don't really think about it very often when it all works. We write this, and at some level, certainly in the back of my mind, I'm kind of expecting that the hardware is running that program, kind of as it is. But there's all these levels in between. Oops. Come on. There we go. So, three of the commonest places where you come across assembly are interactive debugging. Who's ever come across some assembly in GDB or Visual Studio? And what did you really want to see? Probably not assembly, source code. And so one of the questions is, how can you make sure you see source code? And when you can't see source code, how can you get there? And we'll cover a little bit of that. Checking compiler optimization. Who's ever checked the output from the compiler? Yeah, to say, what did the compiler make of this? Can I make it faster? Maybe. How easy is it to tell? Not very. But it is quite fascinating sometimes to look at some code and then look at the assembler and say, good grief, how did it turn that into that? And then you can fiddle with compiler options or change your source code and see what happens on the other side. And then just generally, part of knowing stuff. How does this program work? What's going on under the covers? What sort of mental model have I got of my program? And if it does go wrong, how can I kind of unpick it and work out where it went wrong and how I got into this mess in the first place? So let's start with the x86 architecture, which has been around for a very long time, too long to worry about. What the CPU knows about life. I have this kind of thing. I think about the inside of a computer. It's quite dark. What's the chip know about life? Well, it's just got some pins sticking out. Nothing much. It can access memory, and it's got registers, internal sort of scratchpad values. And that's basically it. Not much else to think about. When the x86 first started, it was a 16-bit processor, which was a great step forward from 8-bit processors, but seems pretty old hat now. And it had a set of registers, general registers, A, B, C, D, and then they went to S, as you do. They had a very odd instruction set because several instructions actually were targeted to specific registers. So although they were called general purpose, they weren't very general purpose because certain instructions only worked and implicitly worked with one or two registers. But we had these kind of arithmetic registers. And then additionally, for memory accessing, there were these segment registers, which fortunately you can now forget about. And you've got IP, intellectual property. No, wrong acronym. The instruction pointer. Where am I? What instruction should I be executing next? And a flags register. So when you did a comparison or a subtraction or whatever, the flags register would have various bits set to say, yes, the calculation resulted in a negative value or overflow or various other conditions. And that's basically it. And the memory model was very simple. You had a segment, an offset, you multiplied one by 16, added it to the other, that gave you an address, and that was an address in physical memory. Nice and simple. And there are a lot of other details that are not really relevant for this purpose. Additionally, 4 of the 16-bit registers could be accessed as 8-bit, high and low, H and L, because they were looking at making it possible to port things from 8 bits to 16 bits. And also there are times when you wanted to break the register value down into smaller bits. And you might wonder, why on earth am I talking of all this history? Well, the thing is that the modern chips have got that history, and they're based and built on top of it, and a lot of the stuff that was written way back is still there in the way that the x64 chips operate. The next thing that happened is the 8087. Anyone remember that? You're showing your age. Yeah, I do as well. Math coprocessor. Could do floating point numbers on a second bit of kit that probably cost as much as the computer that you put it into. And they added these extra register stacks, ST0 through 7, that held floating point values, which were 80 bits. So you did your stuff in your CPU, you squirted a value off onto the register stack, you did stuff on the 8087 at 80 bits, and then you typically got 64 bits back. What could possibly go wrong? So depending on how many round trips you made, you might have lost a few bits in the calculation, but you know, it worked really well. And then 16 bits, alas, for Bill Gates' famous quote, was not enough for everyone, and we needed to go bigger, so 32. So all the registers were extended. So the new registers, 32 registers, had an E in front. EAX, EBX, etc. And a couple more segment registers were added. So you got C, D, E, F, and G. The instruction pointer became an EIP, and the flags became E flags. But just for fun, the old names of the registers were still there, so you could still access the 16-bit values in the low half of a 32-bit register, which again meant that you could take your old 16-bit code and it was much easier to get it working in a 32-bit world because it basically just did what it did before. And the extra 16 bits were irrelevant most of the time. And then, of course, what comes after 32? 48. No, 64. So we go up to 64-bit registers. So they picked R. I don't know why. R for register. Or really? So we've got RAX, RBX, etc. And some new registers. This is nice. The 32-bit world, we just had the same register numbers as before, just they were bigger. Now we've got a whole bunch more. And rather than this funny naming convention with A's and B's and SI's and DI's, it's just 8 through 15. So this means we've now got a lot more places to play around with registers. What's good about registers? Very local. Yep, they're actually on the chip. Can't get closer than that. So if you can do all your calculations involving registers, things run much faster. What's the downside of registers? Only a few of them. Yes, you really want hundreds of the things, so you can just load everything out of memory into registers once and be done with it, and then forget memory, because it's so slow, and just get on with it on the chip. So at least with an extra 8, things are looking up. And one of the complaints back in the day with the 32-bit and the 16-bit world from the compiler writer's point of view is it was really hard to optimize because there were so few registers to play with, and you had this thing called register spill, where you need another register, and they're all in use, so you've got to push one out into main memory. Well, cache anyway, but to make room for another one, and that becomes less of an issue with the extra 8. Of course, no one's ever satisfied. You always want a few more, but it's better than nothing. And once again, we've got the old names still available for accessing the low 32-bit values. So you've got a 64-bit value that can be read as RAX, or as EAX, or as AX, or as AH and AL. There's quite a lot of aliases, effectively, for the same number. The new registers were 64-bit. They're new, they're 64-bit only. But just because it's useful sometimes, you can access the low half of those with a D. So DR8 is the low half of R8. Fortunately, you don't really care about that because that's the compiler writer's or the JVM writer's job to worry about how to map your high-level stuff down into registers. Meanwhile, things were moving on elsewhere. The floating point register stack got overlaid with these MMX registers. Who's used MMX registers? A couple of people, yeah. And for reasons I don't quite understand, they decided, probably to save chip space, that you can either use the MMX registers or the floating point stack, but they're basically the same bits of silicon, so don't try mixing and matching because bad things happen. Then they added 8 new 128-bit registers, which then became 16, and then got widened to 256-bit YMM registers. Do you take this pattern with the alphabet going on in this? Yeah. So no surprises, there's now ZMM, 512. Of course, now a hosed, because what comes after Z? I don't know, I'm waiting to see. We may get there. So you've got these 32Y, 32Z, loads of registers. Plus, I'm not even covering all the process control registers that actually mostly are run by the OS, or the registers that manage things like virtualization. You've also got a whole load of debug registers, instrumentation registers. Fortunately, those are not ones you're likely to see in the code that you as an applications programmer are likely to be looking at. So we can ignore those for the purposes of today. Don't panic. Because although there's lots and lots and lots of complexity, a bit like the 80-20 rule, most of it you can ignore most of the time, or at least just approach it when you need to. So what I'm focusing on is scratch all the control, debug, and performance registers. Don't worry about the segment registers, because in the standard Windows and Linux programming model, they're irrelevant. They're all set to the same value pretty well, and they don't add anything to your understanding of what's going on. So although they're there and the debugger may display them, you don't care. And don't worry about those, certainly not to get started. The next thing we need to think about is what happens when you do function calls. So if we think about our Hello World program, we stream stuff out to cout. That involves doing sort of function call. And the way that most stack-based languages work is you have the idea of a stack frame. So somewhere in the whole heap of memory that's your stack, collection of memory, you've got the idea that this is my bit for my function. And it's laid out somehow. So that I've got scratch space for things like local variables. Somewhere I need to know how to get hold of the arguments that were passed to me by my caller. And somewhere I need to assemble the stack for calling down to the function I'm going to. In the 32-bit world, there was some other information that was held in there, particularly to do with exception handling. But that's not the way it's done in the x64 world. So when you call a function, first thing you're doing is you're calling something else. You're changing the instruction pointer to somewhere. But when you finish, you're likely to want to come back. So one of the key things, obviously, in any stack frame is, where's my return address? Where do I go back to? And what arguments was I passed? In principle, in theory, they're all part of your stack frame. And then as I execute my function, I want to have local variables, int I, int j, char star p, set them to various values. They've got to live somewhere. They live on the stack frame. That's the sort of simplistic picture. So I've drawn a nice picture which bears no relation to reality in most cases. But this is what your kind of starting point is. So somewhere in the frame for my function, I've got a pointer to the previous stack frame. Because when I finish my frame, I need to hand back to my caller the environment that they had. So they're stacked up one on top of another. And typically, you have then the return address and then any function arguments above it, and then local variable space below that. And then when I make a further call, I start here, and I push arguments and call down. Except when I don't. Because what happens if you access the stack? Where is the stack? It's in memory. Memory's slow. I don't want to have to put things in memory if I can avoid it. So the 64-bit calling convention, most arguments are passed in registers because it's fast. And you've probably got it in a register anyway to generate the value. And the conventions, of course, as Tannenbaum said about networking standards, the great thing about standards is that you can always have one more. There isn't a single 64-bit calling convention. There's two main ones. Linux uses one, Windows uses another. They're similar. If you sort of squint at it right, they're not that dissimilar. They both use a register for return values. They both have the idea that there are certain registers that you had better not fiddle with, or at least if you do, you better put them back to the value they had when you finish and return. Because that means from the caller's point of view, they can rely on certain register values remaining the same over a call. So they haven't got to save all the register values away somewhere safe, make the function call, and then restore them. The caller, and again, it's not normally you, it's the compiler on your behalf, knows that a lot of the registers you've got will be restored when the call completes. They define which registers are volatile, which means if I call a function, it may scribble on these register values. So I can't rely on them being retained. So a real stack frame, actually compile it and have a bit of optimization, might look like this. What's missing? Well, there are no parameters being passed because they came in registers. The first 6 arguments in the Linux 64-bit one, DI, SI, DX, CX, R8, R9. Now that is a list worth having somewhere to refer to. Because if you're inside a debugger looking at a function, and you want to know how to relate the numbers you're seeing in the assembler and on the registers to what you've got in the source code, that's the first argument, that's the second argument, that's the third argument, etc. Well, at least it is when you enter the function. What happens after that, of course, depends upon the assembler code. The second thing is, the other thing that's missing from this one, go back. I've got the saved RVP. Well, people notice that actually inside the function, I don't need to worry about setting a separate register up to be the stack frame pointer, because the compiler knows what it's written, and it can just base it all off the stack pointer. Because the base pointer will be somewhere around here, but the stack pointer is a known offset from it, and as the stack goes up and down, the compiler can do the arithmetic and say, oh, that variable that was at stack pointer plus 18 is now at stack pointer plus 24, and then do a bit more, now it's at stack pointer plus 20. So it doesn't need an extra register, a whole register just for holding that. That's pointless. I can use it for other, more useful stuff. So very often you find there is no actual register holding the address of the stack frame. It's kind of inferred. And the other thing is you may find, it's less common in Linux, but if you push things onto the stack, you're doing two things. First of all, you're writing something to memory, and the second thing is you're changing the stack address, which makes it trickier for pipelining. If the next or a subsequent instruction also uses the stack pointer, it's got to wait for the calculation of pushing the stack pointer before it knows what value it can use, unless it's clever enough to say, I'm accessing something off the stack pointer, but in between where we are now and where I am, there's an instruction that there's a push. So that's going to mean that the value I'm going to get by the time it gets to me will be 8 different from what it was. That's quite complicated. So pipelining is a bit harder if you're using the stack a lot. Whereas if you move things relative to the stack, So you want to populate things in here, you can just move into stack plus 16, stack plus 8, rather than having to push and pop. So it means it can be a bit tricky if you are presented with this in the debugger, working out what's going on, where things are. Fortunately, as we'll see, there's information available, metadata, that lets you, or lets the debugger work that out for you. And it's similar, but slightly different on Windows. The first thing that's a little weird on Windows is you get 4 entries reserved on the stack, which is where you can put, or could put, the 4 arguments that come in registers. It's 4 in Windows, not 6. I don't know why, just is. CX, DX, R8 and R9. And in a debug build, typically the first thing that the compiler does is it puts those 4 register values into those 4 addresses on the stack. So it looks as if they were passed on the stack, which means you can find them easily in the debugger. And also, it doesn't matter what happens to the values of these registers, the value you had on entry to your function is sitting in that location on the stack. So it makes debugging programs in a non-optimized build much easier, because the values that you had on entry to your function are still there the whole way through the function, and when you exit, whatever's happened to the value of these registers. Of course, when you turn on optimizing, the compiler doesn't guarantee any of that, and it's just as likely to use these 4 reserved entries for its own scratch space for who knows what, which is why it's much more difficult to debug an optimized build. As above, though, the frame address doesn't need to be saved, and it's very common in, certainly the Microsoft compiler on Windows, that what it does is it works out the largest amount of stack it will need at any point in your function call, and it just sets the stack pointer down to that. And the stack pointer doesn't change after that point, the rest of your function. It just does a call from here, and it's just moved any stack-based arguments into the right place on the frame. Now, in terms of instructions, there are a lot of instructions in the x64 assembler. And what they've done is they started out with a fairly small set of slightly wacky or non-orthogonal instructions. And then as time's gone on, they've found increasingly obscure corners where they could squeeze another set in. And a bit like the periodic table, which has got this kind of, you know, little bit down the bottom and there's 2 lines that sort of fit in somewhere else. They've done the same with the instruction set. So you have a prefix, which was a previously unused opcode or set of opcodes. And the prefix says, well, what comes after that now is a whole slew of extra instructions that do something else. So one of the consequences is that x64 instructions can be of a wide variety of lengths. 1 byte, 2 bytes, 3 bytes, 4 bytes, up to, I think it's 15 or 16 is the longest possible instruction, which is a bit weird. And if you're trying to, again, look at, you've just got binary data, where are the instructions? Well, they're of different lengths, so it's very hard to tell. And if you start out at the wrong place, you're just turning random numbers into instructions, which probably works because nearly everything could be an instruction. I'll show you an example of that later on. Fortunately for bluffing, the vast majority of the assembly instructions in most compiled programs come from a much, much smaller set. So if you learn 4 or 5, you can at least get the sort of geography. It's a bit like navigating around a big city. You know, if you know where 4 or 5 places are in London, you don't need to know the detail because you can just work the rest out by inference. And it's a bit the same with assembler. If you know a few instructions, you recognize your friends, and the ones in between you can look up if you need to, or guess. So I took the disassembly from 3 different binaries and just ran it through, did a bit of grepping and awking and searching, and discovered that in the cases I picked, 50 to 60% of the instructions in the decompiled output were 3 instructions. So that's half of the output is just 3 instructions. And 90 to 95% was covered by about 20 instructions. I must admit, I was quite surprised by that. I thought it would be a bigger footprint. But that's quite, I find it quite encouraging. I mean, you guys may not, but I did. You probably can't see this, but the picture shows it all. Distribution, and it just sort of drops really fast. And then you've just got this long tail that goes off for quite a long way. And it will depend, of course, what sort of instructions you're looking at and what sort of program you're writing and what your compiler and optimization options are, and whether you've specified the wacky flags to make it architecture specific. So, you know, your mileage may vary, but the same principle is true that most of the work of your program is done by the extreme right-hand end here. So in my case is the top 3 instructions. Do it as a roll call, start at the bottom and work up. We've got mov. Remember when Unix, you know, why use 2 characters when 1 will do? It's a bit the same here. Why use move when mov will do? But it's what it means. Roughly equivalent to an assignment. You're assigning one value to another value, moving stuff around. The source and target might be a register, or you might be loading or storing stuff out of memory. LEA, load effective address. That's a weird one. We'll come across that later on. And then call, make a function call. Lots of those. Oddly enough, there's quite a lot more calls than there are returns. If you think about it, it kind of makes sense because you hope to write functions that are reused, so you'll have more call sites to the function than you will have return statements. And the target for a call, again, there's multiple addressing modes in x64. The target might just be held in a register. That's nice and simple. Or it might be an indirect address that itself holds the target of the call. But when you're looking at the assembler, you don't probably care too much. As long as you can work out where it's going, exactly how that mechanism works isn't directly relevant. Sadly, however, we've got 2 different, probably more than 2, but 2 main different ways of showing assembler. The Intel and AT&T is how they're most commonly described. So on the left, we've got the AT&T, which I think came from a completely different hardware platform, and they just had an assembler syntax for that platform, and it's just been generalized to all the various places that GCC in particular has ended up. And their convention is that you use dollar around kind of literal values, percent around things like register names. The mnemonic includes a letter which indicates the size. So mov is the standard native move, which is 64-bit. Mov L is move a long, a 32-bit value. And then the addressing modes, they use round brackets. So it's hex 44 bytes before whatever it is that that register is pointing to. Whereas on the Intel format, they do it the other way around. There's no escape for the registers, it's just RAX. And it's move into that from that, rather than move that value into that target. Which seems most natural to you will depend on stuff. You know, you might think one of them is really, really sensible, another one is completely barking mad, and the person next to you probably thinks the same, but about the other way around. And you just have to learn which is which. I'm reminded of when I was learning New Testament Greek, and there was a wonderful phrase in the book. It said, the distinction in Greek between coming and going is less nuanced. And I thought, I visions all these Greek people wandering around, not sure whether they were coming or going. In general, this format is quite common on Linux, but it is becoming more common to see the Intel format. And this is the one you tend to get on Windows. So GCC, for example, you can output the in either format. With Microsoft's compiler, you don't get the choice. You just get this format. So if you're using GCC, you've got a choice of which you would like to see. So let's have a think about move. The move instruction can do some simple arithmetic when it's calculating the addresses. So it's not just as simple as, here's an address, move from that address to this register. You can say, here's an address, move from this address plus 4 times the contents of that register plus a constant. And that's done by the microcode on the chip. So your attempts to be really helpful to work out the register value, the pointer value yourself in code and use that might actually be making sure you can't use the extended addressing modes that the chip will do for you. So if we've got a structure like this with a couple of int values in it, and we have a pointer that points to one of those, then accessing some array index into P could make use of that expression. So we've got an address, which would be P in this case, plus 4 times plus, because that's the offset, another one times 8. So we've written code like this, and the chip is executing code like that. So there's no need to try and be clever and optimize necessarily by saying, oh, I could save the chips and work. I could work out P plus IDX myself and call that a variable Q, and then access Q plus something, because that would be faster, right? Possibly. On the other hand, you're now adding to more registers. There's only a few registers floating around, so you might have actually made your program slower by attempting to optimize what it's doing. So simple data structures, small data structures, and simple integral indices, the x64 assembler can do a lot of that work for you, which is quite nice to know. Some other popular instructions. We do a lot of checking if, for, while, any of the kind of flow control. And they tend to end up coming down with a test or a comparison of some sort, which take 2 operands. And basically, one of them is doing a bitwise comparison. It's a bit like an AND. So you test a set of bits in a value. And the comp one is like doing a subtraction, but no actual result occurs. It just says what would happen. Is this value bigger than this one? Push and pop, which do 2 things. They write a value into the stack and change the stack pointer. And pop just moves the stack pointer. Jump, goto. Yay, who's used goto in C++ recently? Well, recently, no. But obviously under the covers, that's what the compiler's generating from this lovely structured code you've written in C++. Loads of it ends up being jumps, gotos, under the covers, which I also think is kind of ironic, given how bad a press goto's got. But the code's doing that effectively beneath the thing. And again, like with call, the target address might be indirect, it might be an offset, it might be held in a register. And then add, subtract, multiply, and divide. Like I said, you can sometimes guess what these things do. So how do we get assembler? Well, you can start and write it with Notepad or VI or Emacs. I'm not going into that debate either. Who's written assembler back in the day? Yeah. Would you recommend writing your latest program in assembler? No, I thought not. There are very few times when you need to use it now. And besides, it's very hard to bluff, because when the assembler reads your source code and just burps, it's obvious you don't know what you're doing. Plus, there's a whole bunch of metadata you've got to get right for most assemblers. You can't just start writing assembler. You've got to set up kind of stuff at the beginning and tell the assembler what kind of thing you're generating and wave some hands at, is this code, is it data, what names? Don't go there. But typically, when you're compiling high-level language, you've got a flag somewhere on the command line or in the IDE that lets you generate assembler output from your lovingly crafted source code. Who's ever used that? Yeah. Who's ever found that the output is very, very hard to make any kind of sense of? And it's quite long as well, yeah? The GCC guys are quite keen, if you report a bug, that you send the intermediate file, not even the assembler, but the intermediate file. And there's a limit on how big those can be, and it's quite easy to break that. And if you're looking at the assembler output, again, it just goes on and on forever. But we'll look at some techniques you can use to make that simpler. The other problem is the output may or may not be complete. In particular, the output from GCC, you can pass through GCC again in assembly mode and actually get the same binary, but the Visual Studio output can't be passed through their assembler. I don't know why. I suspect it's a bug, or at least a feature, but it's a bit of a shame because it means you can't tweak the assembler and reassemble it. The next place you're likely to come across assembler is when you're disassembling binary data. Typically in a debugger, but not necessarily. You can run various tools that take a binary of some sort, executable program, and generate you the disassembled output. Sometimes they get it right. Sometimes they don't, because people do weird stuff in code, compiler writers do. They put tables into source code. So if you've got a switch statement, it may end up as being a jump through a jump table. Now, if you try to disassemble the jump table, you're going to take these random offsets and attempt to interpret them as if they were assembler instructions. Who knows what you'll see? So you've always got to treat the output from a disassembled output with a little bit of skepticism. This may not quite be what you think it is. And the problem tends to come where, because of the variable length of instructions, if the disassembler starts reading and gets confused by something that isn't actually an instruction but is merely data, it may take a while to resynchronize with the true instruction sequence. So that, again, is something to watch out for. So here's a couple of examples with G++. You can just do -S, and you get, in this case, with that hello world, that 4-line hello world program, generates a mere 98 lines of assembler. But I can actually pass that through GCC and get the executable out again. Yay! Whereas with Microsoft's compiler, I get 6,704 lines of output from my 4-line C++ program. The reason being is that an awful lot of the things I'm calling are inline. So IOStream is pulling in shed loads of template stuff that's being compiled and is appearing in the assembler output, which I'm probably not that interested in, but I've got to wade through it to find the little bit of code that I wrote. And you can't assemble the output with ML, which is sad but true. But in both cases, finding the actual opcodes I care about can be non-trivial. Some tricks people use, one of them is that you can have a volatile global variable and you access it, do your stuff, access it again. And then you just search through the assembler for that name. And then you've got the kind of bracketing for where your code goes. That can work quite well. Another way of doing it is to take your code under test, make it a function, and then have, again, typically using a volatile function pointer to that block of code. So again, the compiler can't optimize it, and because it's a separate function, you've got some hope of finding it. But you give it a strange name, which you won't find by accident in your code base. A hint, calling your function test is a bad choice. How do I know that? I'm not telling you. So here's an example of coming across some assembler when you didn't really want it from GDB. That's the bit you don't want. No source available. Oh dear, that's a shame. I'm on my own now. I think I was just debugging, I can't remember what it was now, it might have been the command shell. I just kind of ran it up and broke it and got into it, and there I was. And I can attempt to set layout, source, layout assembler, and the assembler gives me something, but the source doesn't. And I'm kind of thinking, okay, where am I? How did I get here? How can I get out of it to something I understand? Where did I come from? And those are the kind of questions. And what I'm being given is, I'm here in a process I've got a function name, that's good. That's the program counter. For reasons I don't fully understand, IP, the instruction pointer, or RIP, is always known as PC, program counter. It's a shame they can't synchronize those names and just use one consistently, but and again in WinDebug on Windows, you get very much the same. Here's again a command shell. I put a breakpoint at main, and here I am with assembler. And here I am with lots of mov and a few push. Oh, good, I know those. That's easy. Again, you've got a choice very often when looking at assembler. Do you care about this lot? Hey, it's hex. Probably not. And many of these tools do give you a choice as to whether you do or do not see the opcodes. Of course, I'm assuming that's code, and it probably is because it starts with main, but if you look at the hex values here, 41, 55, if you're enough of a train spotter, you recognize those as ASCII codes, right? So it could just be a text string of some sort that I happen to be disassembling. Not in this case, but in general. You've always got to be aware with assembler that there isn't actually a hard and fast separation in some senses between code and data. If the instruction pointer happens to hit that byte, it will interpret the next 2 bytes as an instruction. But if it starts to access code here, it will attempt to process 55, 41, 56, whatever that is, as an instruction. And in particular, it's very hard to go backwards. Because if I come back. Hello? That's the one. If I didn't have and I was just here, how do I know how long the previous instruction was? Ooh, that's tricky. Well, let's see. Maybe it was a 1-byte instruction. Look up 10. Is 10 a single opcode? No, it's not. Right. Is 6810 a 2-byte opcode? I have no idea. It might be. Is 896810 a 3-byte opcode? And you basically work your way back up to sort of 16 and see whether any of those might be an instruction of the right length to end here. And there might be multiple answers. So assembling backwards is difficult. A bit like, you know, the well-known missing come from instruction. You know, how did I get here? There's multiple routes to a destination, and you don't necessarily know which one it was. So very often, if you're trying to work out, and all you've got is a core dump, and you're not quite sure how you got there and what's going on earlier, you find out what function you think you're in, and start at the beginning of the function and work downwards, rather than trying to backwards do the disassembly. So here's an example of what happens when you just change the starting point. So I took that previous command shell output and I just started to unassemble at RIP plus 5. So 5 bytes into the function, which can happen if you've got memory corruption and you end up going to a random location. And the next 5 instructions are completely made up. There is no instruction like that there. That just happens to be what the disassembler made of the byte sequence it found at that address. And it's not until 5 instructions later that we get back to on target, on track with what the original code looked like. Now sometimes you're lucky and it happens much more quickly than that, and sometimes you're unlucky and it stays out of step for a long time. Fortunately, in the vast majority of cases, it just works because the instruction pointer you're starting with is actually a genuine instruction pointer. Something's going wrong. So, first off, assembler, just say no. Know how to get source code. It's much easier. In particular, check your tool chain. How does your tool chain let you build with symbolic information? How does your tool chain make sure that it's associated correctly with your binaries? It's all very well to generate the symbolic information, and then you're actually debugging a problem on a production box. Where's the symbolic information gone? And it's worth quite a lot of effort to make sure you've got that information available, and you capture that with your build process so you can go back to source code. And various of the tools, I mean, Microsoft Symbol Server and Source Server let you associate with a version repository so it can actually go back to a particular version of the source code in your repository that was used to build the binary you're running. So you're not having to kind of guess whether the source code you've got currently in your local repository bears any relation to the source code that was used to build the binary. You can actually capture that information in the binary itself. Unfortunately, even in this day and age, you can run out of disk space. A couple of contracts ago, we were trying to do, for good reason to do with performance, building separate executables with just the bits in we wanted for performance. So it was big fat executable, no shared libraries, because you get a measurable performance improvement by doing that. But it meant we had, I don't know, 16, 20, 50, 60 megabyte binaries. That's without debug information. With debug information, they were like 500 meg each. So each build was about 5 gig. So you run out of space on a continuous integration server more quickly than you might like. So you've got to find ways of managing this sometimes. Buy a bigger disk, that's one option. Split out the debugging information. Most environments, GCC and Windows let you separate the debug information from the binaries, and you can keep the debugging information in one place, squirrel it away for if and when you need it. There are also ways of reducing the amount of information you get, so you might be content with just information about line numbers and source code, and not be too fussed about local variables. And find out the options for debugging system libraries and your operating system and any third-party libraries you've got. And again, do that before you're debugging your first live production problem, because it's worth checking it really works. What I find very often is you do the development on your own machine and everything's great, and debugging is easy because everything's local and the one you built is the one that's got the source code. And you think you're done. And then you have it running in the UAT environment and you get a crash. And then that's when you start discovering whether you've actually got the tool chain you need to let you debug it there. And it's very easy to test that. You don't need to wait for a crash. You can just try it. I think this isn't really working very well. Let me... Who's come across Compiler Explorer? Okay, well, you can go to sleep for a bit. This is a wonderful bit of kit. This guy called Matt Godbolt put this together. And what he does is, on the left-hand side, you've got source code. Now, I'm playing around with C++ in this talk, but it does actually support other languages. And on the right-hand side, again, you can configure all the panels, but that's how it comes kind of out of the box. You get little bits of assembler with colors. Wow, what's not to like? I think you can change the colors, but I never bothered. And as you type code in here, what's in there changes. And you can select the drop-down, and you can change compiler to all sorts of other compilers, and you can type compiler options in here. And if you've got the choice, given which compiler you've selected, you can decide whether to go for the Intel or the AT&T syntax. The clever bit about Godbolt, apart from being on the web, which of course means it's wonderfully sexy, the great thing about Godbolt is he's done the hard legwork to identify where is the code you really care about? Remember I said about the hello world generating about 100 lines of assembler? Well, this again is going to generate a lot of lines of assembler. What you see by default on the right-hand pane is just the bit you care about. He's got a whole bunch of scripts and code, and I've never looked at it, but it does a really good job of narrowing down to the bits of code you're really interested in. And as a tool for looking at and exploring and understanding 64-bit assembler, this is great. So we'll have a play with it in a little bit. So you can specify how often it gets compiled and what compiler options you've got, and you can then, for example, see, well, this code I've written that I've written to be really clear and obvious, does the compiler optimize it well? And even if all you do is say, let's count the instructions on the right-hand side. And what happens when I turn different optimization levels on? Even better, you've got the support for many different compilers. So you can see whether Clang and GCC do the same sort of thing, whether it works better on Visual Studio than it does on GCC or vice versa. But even better, you can fetch it from Git and you can run it locally. And it automatically out of the box, I was really impressed by this, it finds all the local compilers. So I ran it on my, I downloaded, I'll show you in a minute what I did, downloaded and set up a virtual box on my Windows PC. There's two things you need, npm and node.js, which I had to install. And then you just get the repository out of Git and you type make. And it does the rest all by itself. Brilliant. And you can also configure non-standard locations. So I downloaded GCC trunk and built that, and then just edited the config file to tell it where GCC trunk was, and it just works. So that means that I can run the demo on my laptop without having to worry about whether the internet for the hotel's working. But also it does mean you've got options in environments. Who works in a place where you've got unfettered access to the interwebs? Ooh, you lucky people. Yeah. Who works in a place where the internet is something of which you hear when you leave the office? Yeah, there's a lot of restrictions on whether you could put your company's source code on an online compiler. Be very careful trying that, because you might discover it's the last thing you do in your current employer. I nearly lost a contract when I sent a 20-line sample program that demonstrated a problem with the Windows API, emailed it to myself at home, and my manager got a phone call at 7 o'clock that night from the automated software that I was emailing software out of the company. It's like, it's int main and it calls a Windows call. He said, yeah, but just don't do it again. But with Godbolt, you can get that into the company, and then you can do your own playing around with your own source code locally, with your own settings. So that's all I did. Got VirtualBox from here. Oh, I installed Ubuntu in it. Got npm, node.js. I only got Git. And then just pulled down Compiler Explorer from Matt Godbolt's site on GitHub. And then type make. And then dark purple on blue was a bad choice, wasn't it? I should have changed that. And you just go to localhost 10240, and there it is. And then I did a sudo apt install Clang and restarted Godbolt, and it now had Clang as another option, which is pretty cool. So this is where it all goes horribly wrong, because I tried to demonstrate this. Oh, that looks just like the slide, doesn't it? There's a reason for that. So, looking first at the program, we've got the light green on the right, we've got some yellow, and we've got some grey. Anyone hazard a guess as to what the colours are about? Stack frame. Yeah, what we're doing first off is we're setting up the stack frame. So this is non-debugged, non-optimized. So we're just saving the current stack frame, RBP, saving our input argument. The first argument comes in a register, EDI. Saving that away. The yellow is the guts of the function, which in our case is pretty small. And then the grey is the epilogue. So we've got a push of the stack frame and a pop of the stack frame and a return. It's a very, very simple example. This doesn't call anything else, doesn't use really any local variables, so all three sections are quite small. In between, we move the value into register, and then we multiply the value. I was doing that before. I don't think it's anything to do with the microphone. The other nice thing is, hopefully it will work, it might not. In theory, if you mouse over, it's not going to work, is it? No. Something's not working. Normally, when you mouse over, you get a nice little pop-up box that talks about the instruction you're mouse overing with a link. Unfortunately, the information is not always completely up to date, and some of the really new instructions that you might end up with aren't on the list, because whatever website it's going off to doesn't obviously have all the latest information up to date, but very often it has enough information on the mouse over that when you come across an instruction, if you couldn't guess what imul meant, then, as I said, normally, mouse overing that and it would tell you it was an integer multiply. Yeah, it's probably not able to get out from my box through. It worked at home. But, and if we wanted to look at the other format, now which do you prefer? First or second? Up to you. You've got a choice in this case. I've used the Intel format for longer than I've used the GCC AT&T, so I prefer the other format. But they're both the same in terms of, you know, it's much faster now because it's got a cache, so if you recompile something, it just sort of saves it away. Well, let's see what happens if we add a bit more code. And if we do, I thought you watching me type would be really pointless. So I now put in a call to my function. And again, it does the smart stuff, throws away all the stuff I'm not interested in. If you actually look at the raw assembler, there's more in it than that. And it just puts in the call. So now I've got setting up the stack frame again for main. And then I've got the function call, and I've got the epilogue from main. And you can see here very clearly that it's moving a fixed value into a register and calling function. So you can kind of put the bits together and see it happening in your head. The return value comes out in EAX. Yeah. Yeah, I probably should have done something with the return value. Since main returns an int, again, it doesn't need to do anything with EAX because that will just pass out of the end of main, and the return value from main will be whatever the return value from square is, which is quite nice. So if you're debugging this with a debugger, and I've put a breakpoint somewhere in here, when the debugger reaches that breakpoint and stops, it can work out from metadata in the binary that I'll cover in a bit, exactly where in the debug build the argument was, because it's been saved nicely in the stack of that BP-4. So it can display the value of the local variable. It can know where the saved stack frame pointer, RBP, is, so it can work up and find out who called it, and it can do the same calculation there to show what the local variables were in its caller, and repeat. Again, because the calling convention mandates non-volatile registers must be preserved, some of the metadata in a called function will be where have I put the non-volatile registers. So the debugger can look in that location and restore, in your view, what the non-volatile register was in the caller. And again, working your way back up the stack. So you can get a lot of information out with a debugger that knows how to poke around at these metadata that you could do yourself, but why? It's the sort of thing, it gets right, and you need a wet towel around your head and a kind of pen and paper to get it right. And it's much, much better to use the tooling for those sort of things. So let's see what happens if we do a bit of optimization, just one. Well, the first thing you notice is it's smaller. That's blindingly obvious, whatever else you know. The second thing is, where's all that stack frame stuff gone? Who needs it? So main doesn't bother with a stack frame because all it's going to do is, it's going to just move 16 into AX. Oh, hang on, what's going on here? Well, the compiler, it's been asked to optimize. It can see the implementation of square. It can do that for you. Well, that's a shame. I really wanted to see what it actually did. Well, the answer is it actually does that. It just returns 16. As it happens, I've still got the code for square up there because that's needed in case I link this against something that calls it in a way that can't be optimized. And all that does is it just moves the EDI into another register, multiplies it, and it's done. It's in the right place anyway. It, again, doesn't need any stack frame. So if we much the same. Much the same. In this particular case, it doesn't matter what you do, you can't really get much better than that. But in general cases, we'll find, and we'll see in a bit, that it does get a lot worse. One way of solving this, optimization, taking out the very code you're trying to look at, is by using some sort of variable to indirect your function call. So if I put need to do a and now I say, I don't want to call square by name. I want to go via a volatile function pointer. So the compiler is not allowed to optimize that away, just in case it changed between when I initialized it and when I read it. And so now I've got in my calling code what happens when I actually call the function with an argument that I didn't know at compile time. So it moves the address of the function into here, and then it does, this is one of the places where call goes via a register. Let's call the contents of whatever's in our AX. But the same thing as before, I've moved 4 in and done the call. And in this case, when we optimize it, we'll get slightly less, possibly, surprise. So again, it's removed a little bit of the function prologue. Certainly that's gone, but you've still got the call in there. But actually, we can be a little bit cleverer. And if we bump the optimization up a little bit more, I think it's 2, it's taken the call and made it a jump. What's that called? Anyone know? Tail call optimization. The last thing you're doing is calling a function and you're returning its return value. Well, you don't need to bother with doing a call return, you can just jump there. And when it returns, it will go back to your caller with the value. So it just does move, move, and jump. That's it. One other example of something that demonstrates the LEA instruction I'll take a much simpler. So I've got on the left add 1, and on the right it does this LEAL, load effective address. The effective address instruction is a very strange beast, as I mentioned, and it can do simple arithmetic. And it basically does a memory address calculations, but without touching memory. Okay, and what's the point of that? Well, the x64 mode has got this, you can do offset plus a multiplier 1, 2, 4, 8 by a register plus another register. So you can do quite a lot of arithmetic with just the LEA instruction without needing to do actual add and multiply instructions. Why is that better? Well, multiply is generic, multiplies two arbitrary values together, whereas the address modes are designed to cope with just 1, 2, 4, 8. They're heavily optimized for those particular multiplication values. So if you're multiplying by 8, it's much more efficient to use the LEA instruction than it is to do a multiply, oddly enough. And it's very flexible. You can put the output in various different places. You can take the input from various different places. And also, it doesn't affect the flags. So I can do a comparison, and in parallel to that, the next instruction could have been LEA, and unlike add, multiply, etc., it doesn't change the flags, and I can then check the comparison later, and the pipelining can mean I'm doing more than one thing at once, which is one of the reasons why in 64-bit mode, you tend to see quite a lot of calls to LEA going on in the assembler, because it's a very versatile instruction. So, for example, a slightly more advanced use, showing more of its features. Return val1 plus twice val2 plus 7 is optimized down to a single instruction, which is pretty clever, isn't it? So small numbers are good. If you tried 43 or something, that's not going to work as well. And the last little example I think I'll look at is here. Let's just start with optimization off, probably, make it clear what's going on. So here we've got a sum less than, numbers less than a given value, and again, you've got a fairly simple function. Prologue at the top in the green, epilogue here. Stuff happens in the middle with the loop. Loop variables L2, L3, they're labels for things. And it's hopefully fairly straightforward to work through and see what it's doing. Again, I think all the instructions in that sequence are ones we've mentioned. So we've got pushes, we've got moves, we've got a comparison, we've got a jump, and an add. That's about it. And then if you optimize it, you get successive cleverer things that the compiler does. So with O1, a lot of the loops just disappeared, and it's all being done in registers. So everything in here is now not touching memory at all. It's just accessing registers. And then you go to O3, and it's like, whoa, what hit me? What's happened here? It's using all the clever instructions. It's optimizing this by doing it in parallel, by using all these MMM registers, that sort of stuff, so it can take your simple loop and generalize it into something far more complicated. Is that what you need? Well, it depends, doesn't it? What values are you going to pass in to sum? If it's sum less than 10, it's probably not going to be any better than the original code. It might even be worse. If it was 1 million, it might be worth it. So again, it can be worth just changing the optimization level and seeing whether you're getting a sudden explosion of instructions. Because you've also got to think in terms of the instruction cache. How big is that? Never big enough. So if I've got bigger code here, it might be in theory faster. I end up having to flush the instruction cache to fit my code in. The end result might be slower. So this, again, gives us a nice tool for looking at some of the changes. I think that's probably about enough on that one. Go back. There. Where's it gone? So walking the stack, I said I'd talk a little bit more about that just to kind of wrap up. So call stacks, very important information. One of the things I like about programming in environments like Java and C# is when you get an exception, it automatically gives you a call stack. And a significant proportion of the time, if all you've got is the call stack, that's all you need. Who's had that experience? Just knowing how you got there is the single most important piece of information in solving many problems. Fortunately, with x64, that's pretty guaranteed to be possible. But in general, it's a hard problem. And the reason it's a hard problem is because, as we've seen, once you start optimizing, the stack use goes away. Funny things happen. Registers get reused. How on earth do I work from all I've got is a stack pointer and an instruction pointer? How did I get here? Well, somewhere on the stack there's a return code, a return address. But which of the possible addresses on the stack holds that return address? Well, I could look at each in turn and see, does it point to code? If so, it might be where I was called from. Or it might just be an artifact. It might be the last time that something got called and that value is still lying around on the stack because it hasn't been reused. So we need a better technique for doing this. So in x64, we have this additional metadata that's held in the binary. And it allows the stack frames to be used at runtime. So the data tells the runtime system for each given instruction pointer, it can find the appropriate metadata. And metadata says, okay, which register and at what offset is the stack frame? And from that, because they've got a known layout, it knows how to find the return address. It knows where the non-volatile registers are stored, again, off that stack frame. And that mechanism is the one that's used for exception handling in C++. If you go throw, where'd it go? Somewhere up the stack. So it's got to be able to unwind the stack in a very, very safe fashion to find the catch handler. And then when it does the unwinding, to find all the bits of code in between that have to destroy local variables. So the mechanism was required to be in place to support various forms of non-local goto, such as try-catch. But the same mechanism can then be used by the debugger in unwinding the stack to show you your stack frame when you get a breakpoint. Now you can do it, I have been told, manually. Write a tool. So the extra data is generated in assembler with some directives. And one of the things that Godbolt, by default, hides is all these directives. You can turn them on if you want. Probably not really trying to do that. But they're not very exciting. And in GCC and Clang, they're all prefixed with CFI. In MSVC, there's no such common prefix, but there aren't that many directives. And most of the time, you don't give a monkeys what they are. It's just magic. And it generates some data somewhere in the binary. Again, magic. That something can find for you. I have written that stuff once when I was writing some code that generated on-the-fly instructions, and I had to make sure that exceptions could go through the generated code. So I had to generate the metadata on the fly. Windows, and there's some Windows APIs that let you set this stuff up, but it's not for the faint-hearted. Fortunately, very, very few occasions where you ever need to do anything like that. Nearly all the time, you're coping with data where the programmer has just written high-level source code and the compiler's generated this metadata. However, it does mean that if you're debugging a crash dump and you haven't got access to the right version of the binaries, it might prove troublesome to walk the stack, depending upon exactly what information the crash dump itself holds. So again, that's something else to think about when you're checking whether your processes work. Get a crash dump file off your target environment and just check that you can actually walk up the stack in the debugger. Because if you can't, you don't want to do it manually. You just want to make sure the metadata is available for the appropriate tools. Yeah. So the data structures themselves on Linux are held in this EH frame data, which you can look at if you do some sort of obj dump on your binary. And there are libraries out there as well to help you unwind the stack. Anyone use libunwind? Yeah, it seems to do the job pretty well. So if you need programmatically to unwind your stack to generate your own information, that seems to work pretty well. So you start with a target address. From that, you get hold of the metadata. From that, you identify which registers are interested and what offsets off those registers are needed. And from that, you work out where the current stack frame is and where the return address is and where the saved stack frame is. And then you go up one level and do the whole thing again. And just keep repeating until you've got the top of stack. On Windows, they're again held in a separate section in the binary called pdata. I don't know why, probably a reason. And that can be examined with a switch, unwind info, on dump bin. And it actually shows you in full gory detail all the unwind information, should you have some strange desire to look at it. There's a debugging method called stackwalk64 in debug help that helps you walk the stack if you actually want to do that programmatically. And again, it works pretty well. There's also a low-level call that's part of the runtime, kernel 32, RTL virtual unwind, which does effectively one step in this process. And you just provide it with the starting point in the data structure, and it unwinds one level, and then you kind of call it repeatedly. And then there's this one I mentioned, RTL add function table, if you really badly want to go playing with it and write your own code at runtime. So, that was a quick Bluffer's guide. Hopefully it was instructive. There's an awful lot in x64 assembler, and if you actually were writing assembler from scratch, there's so much that we'd have to cover. But we don't need it for most of our purposes. We just need a basic understanding of the commonest registers. A bit of understanding of the calling convention, so we've got some hope of knowing where were our command arguments, where did our function get its values from, where's the return value, knowing it comes out in AX, EAX, RAX, whatever, means that you can put a breakpoint at the end of a function and know what the return value was. And a small number of instructions, just so you've got some idea of the flow of control. Moving data around, doing comparisons, pushing and popping, calling and returning. And then most of the rest is just details, and you can fill in, if you need to, what that particular little bit of the assembler is doing. The biggest problem with assembler is that there's so much data, and so automated tools that let you focus on the data you care about are really important, and that's why tools like Compiler Explorer are a really good place if you want to find out a bit more about x64 assembler. You can take some code that you've got, put it in Compiler Explorer, look at the assembler output, go back and forth, make changes, and see if you can understand what's happening, and then try the same thing in a bigger problem with a debugger or disassembly of some real production code. Okay, well, thank you all.